Swayam Prabha. Digital India. Educated India.
In this lecture, we continue about shocks and expansion wave relations, and we try to extend them to the high Mach number limit. You may recall that we wanted to discuss a little bit more about the Prandtl-Meyer expansion fan last time, and in order to revisit that topic, we would once again like to look at this diagram where the approaching supersonic flow was coming at a velocity of v, and after turning through a small angle d theta, there was an expansion of the flow, thereby acceleration of the flow to a higher velocity v plus dv. In order to identify the change in velocity, we constructed a triangle here in such a manner that we had v represented here in the triangle, and the other arm of the triangle represents dv, and notice that it is perpendicular to the Mach wave. The change in velocity occurs normal to the Mach wave, like the way you saw that the change in the flow features occurs normal to the oblique shock wave. Similar things happen over here too, and if you have an angle d theta here, 90 degree here, mu here, then the remaining two angles work out as pi by 2 plus mu over here and pi by 2 minus mu minus d theta at this lower corner, this being the change in velocity. And therefore, you can write this relation by using the law of sines, as we mentioned earlier. We had discussed a little bit about the Mach waves and how to get the Mach angle mu. And then we recall having said that we can show the relation between the change in theta and the change in velocity through an expression like this involving the Mach number. And then if you were to integrate this expression, the d theta being integrated from 0 to theta, where theta is a finite change of that angle, then Mach number would change from m1 to m2, where m2 would definitely be greater than m1 because the flow is expanding. And you can show that this expression over here can be further written in terms of Mach number using a relation like this. When that is plugged in into the integral, then the integral involves an integrand which is given here, and that is called as the Prandtl-Meyer function, which can be further represented in a form like this. The theta incidentally is nothing but the difference of the Prandtl-Meyer function for the two Mach numbers m2 and m1 respectively. We have put the details together once again, and you can say that the steps of the calculations would be like this, that you would be given the upstream Mach number m1 in a given problem, from which you can obtain the Prandtl-Meyer function corresponding to that Mach number, either by using this relation or by using some tables, which again should come from the gas tables, which we were talking about when we discussed about normal shocks. Based on the geometry, you would be able to find this angle. We have named it as theta 2 over here, and the connection would be this. You know the Prandtl-Meyer function corresponding to m1, you know this from geometry, and therefore, you obtain the functional value for the downstream situation. At that point, you do not know what the m2 is, but you can either obtain it from tables or you can try to obtain it iteratively by solving this equation, because it is implicit in M. Once you find the downstream Mach number M2, you use isentropic relations between states 1 and 2 to calculate the properties in region 2. So, these are the steps to be followed. As we already mentioned that the flow is accelerating, and you will thereby find that the static pressure would reduce, so would be the temperature and the density in the second region, the downstream region of the expansion fan. The entropy will remain invariant, so would be the stagnation pressure and stagnation density. Because the flow is reversible adiabatic, therefore, T naught will also remain conserved. So, these are the important facts related to the Prandtl-Meyer expansion fan. Now, we have completed our discussion on normal shocks, oblique shocks and expansion fan, and we are ready to get into the discussion on seeing how they figure in the high Mach number limit. So, when we are now interested to push these equations and see their behavior in the hypersonic or hypervelocity Mach number ranges, but again still keeping some simplifications intact, like the flow will still behave like a calorically perfect gas, which is of course an oversimplification, we will see later. But for the time being, we would like to ignore those complications and see how these equations fare at the higher Mach number ranges. So, we are going to discuss over the next few minutes on shock and expansion wave relations in the high Mach number limit. Here we have shown the velocity vectors upstream and downstream of an oblique shock. And if you recall earlier that we said that when we discuss about the normal shock and oblique shocks, in the oblique shock scenario, we are interested to resolve the velocities into their normal and tangential components, and that is how many of the equations governing the flow across the oblique shock became so much more simplified, and we found that the normal component of the flow behaves identical to that of a normal shock wave in the case of an oblique shock. But here we take another route, we resolve the V2 vector into streamwise and normal components, which we had initially proposed but discarded when we had discussed about oblique shock waves earlier. So, this time we are going to take that route, we will look at U2 and V2 as the components along x and y directions respectively. As we mentioned earlier that calorically perfect gas assumption is taken into consideration, though we are handling high Mach numbers, and here the flow is expected to get heated up due to the aerodynamic heating, but to avoid complications we are for the timing assuming it to be calorically perfect. So, the specific heats Cp and Cv remain constant, the gamma also consequently remains constant. Now, the exact equation for U2 in this case would be given by this relation. Now, as M1 tends to infinity, so you are talking about an infinitely large upstream Mach number, then you can argue that this term would dominate over the -1 term, and therefore, the equation will simplify to this. Though M1 is tending to infinity, this relation it attains a finite value. So, the change of x component of velocity across the oblique shock would therefore be given by the V infinity, which happens to be V1 in this case, minus U2, and the change when scaled with V infinity would be written like this, which becomes 2 sin square beta by gamma plus 1. And if you recall, when we were discussing about the hypersonic small disturbance equations, we had discussed about this issue that sin beta is of the same order as sin theta, and theta is of the order of dy dx, which is the same as the slenderness ratio. So, this term happens to be of the order of tau square, which is a very small term. And if you recall that in the hypersonic small disturbance equations, we had considered or retained only those terms in the equation which were of order of magnitude unity. Therefore, the non-dimensional perturbation velocity u bar dash, which was one of the terms we saw in that system of equations, that should be defined as u dash, which is nothing but the change in u by v infinity tau square, and that would give you an order of magnitude unity term in the hypersonic small disturbance equations. So, we are referring back to those equations once more, which we had learnt earlier. These are the hypersonic small disturbance equations. You may recall that all these dependent variables, they have been non-dimensionalized, and the one with dashes involve the perturbations. So, we were just discussing about this perturbation u bar dash, and remember that this equation was decoupled from the rest of the system. And here comes the definition of u bar dash, which we just tried to argue why it happens to be u dash by v infinity tau square. On the other hand, you notice that the v bar dash happens to be non-dimensionalized as v dash by v infinity tau, which would be producing an order unity term, and why it happens that way we will try to explain further. So, the exact equation for V 2 is given by this relation. As m 1 tends to infinity, the equation would simplify to a form like this, which again attains a finite value as m 1 tends to infinity. This is the change in y component of velocity across the oblique shock, and there was no v upstream of the oblique shock, if you remember. Therefore, delta v is nothing but v 2 itself, and when that is scaled with the free stream velocity, which in our case is v 1, then it finally becomes sin 2 beta by gamma plus 1. Now, sin 2 beta is of course 2 sin beta cos beta, and beta being small, this is an order 1 quantity, this is an order tau quantity, and 2 by gamma plus 1 would produce an order 1 quantity. Therefore, finally, the expression would end up producing an order tau quantity, tau being a small quantity. We often refer as order epsilon quantities when we refer to such small quantities. Therefore, non-dimensional perturbation velocity v bar dash should be defined as v dash by v infinity tau in order to create an order of magnitude unity term in the hypersonic small disturbance equations. Therefore, it is justified to define it this way. Now, you see the difference between the u bar dash and the v bar dash non-dimensionalizations that we have used, which clearly indicates that u dash is much smaller compared to v dash, since both of those non-dimensional quantities are order 1 quantities, because they differ by an order of tau. Let us go to some of the other equations. Here we talk about the pressure ratio across the oblique shock, P 2 by P 1. This is the exact equation, and in the high Mach number limit, we can say that m 1 square sin square beta will be much larger than 1, though beta is small, but since m 1 is extremely large, therefore, this quantity will still be much larger than 1. Based on that, we can say that the expression simplifies like this, and finally, it will be of order m square tau square, if you try to put in the order of the different terms and try to check. Now, this becomes infinitely large as m tends to infinity, m 1 tends to infinity. Again, based on this order, you could think about non-dimensionalizing the p, like we did in the hypersonic small disturbance equations, to get an order unity kind of a term. So, that is left as a homework for you. So, that was the pressure ratio. if you were to look at the density ratio, then the exact equation works out like this. Remember that the exact equations are involving m1, gamma as well as beta, whereas in the case of a normal shock, we remember that it depended only on m1 and gamma. There was no role of the shock wave angle, because in that case the wave angle is always 90 degrees. As m1 tends to infinity, rho 2 by rho 1 tends to gamma plus 1 by gamma minus 1. For air, and if we assume it to be calorically perfect even in those very high Mach number ranges, it will have the value of 1.4, and then rho 2 by rho 1 can be worked out to be equal to 6. That means, at excessively high Mach numbers also, the density ratio kind of saturates to a value of 6. So, it attains a finite value as m1 tends to infinity. Now, if we invoke the equation of state P equal to rho RT, then the temperature ratio can be written like this: T2 by T1 is P2 by P1 divided by rho 2 by rho 1. As m1 tends to infinity, you basically substitute those expressions for pressure ratio and density ratio. You get a relation like this, and this again will become infinitely large as m1 tends to infinity. Now, based on all that we have done till now, we can work out a few more expressions. For example, if we want to work out the pressure coefficient, by definition Cp is P2 minus P1 by half rho 1 V1 square. We take the free stream quantities over here in the denominator, and for compressible flows we generally express it as gamma by 2 P1 m1 square, and therefore, we come to a form like this, which involves the pressure ratio. So, now if we substitute the pressure ratio expression over here, then the final expression for Cp will boil down to this. At this point, if you limit it to a situation of m1 tending to infinity, then this term would become extremely small and therefore would drop out, and therefore Cp will become 4 by gamma plus 1 into sine square beta, which of course attains a finite value as m1 tends to infinity. So, interestingly, you are finding that some of the ratios become infinitely large, some of the expressions become finite, and so on. For example, in the pressure ratio equation that we saw over here, it became infinitely large, but when you substituted the same pressure ratio expression over here in the Cp equation, the Cp equation took up a finite value as m1 tends to infinity. Now, we recall about the theta beta m relation. The exact equation is quoted on top, and then in the hypersonic or hypervelocity limit more appropriately, when theta is small, beta is also very small. That you can recall from the theta beta m curves. You remember that as m1 increases, the curves expand, and therefore, you will find that for a given theta, the beta values are always small, and when we are talking about a small theta, for example, we have a theta of this value, the beta correspondingly also is going to be very small. Therefore, we can write that sine beta is approximately equal to beta, cos 2 beta is approximately 1, tan theta is approximately equal to sine theta, which is again equal to theta, all in radian measure of course. And now, if we substitute those simplified expressions in the theta beta m relation, we get a relation between theta beta m in this m1 tending to infinity as well as small values of theta and beta limit. So, this expression would further simplify to a form like this when m1 tends to infinity. Therefore, when m1 tends to infinity and simultaneously theta and beta are both small, which is true, which we have seen from the theta beta m plot, then there is a very interesting relation coming up between beta and theta, that beta by theta is gamma plus 1 by 2, and that takes up a value of 1.2. There should not be a theta over here, that is a mistake. So, what it basically means is beta is equal to 1.2 times theta, which means that the wave angle is barely 20% more than the compression angle itself. The product m1 theta is often called as hypersonic similarity parameter, and it is applicable for flow over slender bodies. That means, for small disturbance cases, you may recall that when we were discussing about the hypersonic small disturbance equations, I had mentioned that m1 tau is also often referred to as the hypersonic similarity parameter. That and these is practically equivalent. We can show that based on the definition of the similarity parameter k, beta by theta can be expressed through an equation like this in terms of k and gamma. If you look at the pressure ratio can be expressed in terms of k and gamma through this relation, and the Cp again in terms of theta, gamma and k using this relation. Now, these equations for pressure ratio and pressure coefficient are specific to oblique shock and in the limit that m1 tends to infinity. When it comes to the similarity parameter k, the interpretation could be like this, that if you are looking at two different slender bodies exposed to hypersonic or hypervelocity flows, let us say the theta for this case A is 3 degrees and the upstream Mach number is 10, this should not be degrees. So, m A is equal to 10, and then the product gives you a number 30, the m1 into theta. Here the m B is equal to 6 and the theta is 5 degrees, this is case B. Again the product theta into beta gives you 30, which means the k for both the cases is identical, and therefore, if you study one of these flows, you can infer how the other flow would behave. Actually, they would behave identically, considering that the gamma remains invariant and so on. For hypersonic expansion waves, we can show that as m1 tends to infinity, the relation for theta would simplify to a form like this. This is a small homework problem that you can work on and try to work out how this simplifies for m1 tending to infinity. So, if we rearrange, then we can express it as m1 by m2 equal to 1 minus gamma minus 1 by 2 times k. Again, as m1 tends to infinity, we can say that the pressure ratio P2 by P1, which basically follows the isentropic relationship, can be expressed in an exact manner like this, where P2 by P1 is nothing but 1 plus gamma minus 1 by 2 into m square, m1 square on top and m2 square at the bottom, the whole raised to the power of gamma by gamma minus 1. This is true for isentropic flow between two regions 1 and 2, and as m1 tends to infinity, it would simplify to a form like this. Again, P2 by P1 in terms of the similarity parameter can be expressed like this: 1 minus gamma minus 1 by 2 into k, the whole raised to the power of 2 gamma by gamma minus 1, and an expression for Cp, which again is in terms of theta, k and gamma. So, this is the pressure ratio and the pressure coefficient expressions for Prandtl-Meyer expansion fan. Earlier we had expressed them for the oblique shock, now we have expressed them for the Prandtl-Meyer expansion fan for the limit m1 tending to infinity. To conclude, in this lecture we first completed our discussion on the Prandtl-Meyer expansion fan, then we discussed about shock and expansion fan relations in the high Mach number limit. All the way we assumed calorically perfect gas behavior of air. We revisited the hypersonic small disturbance equations briefly, and we introduced the hypersonic similarity parameter. Thank you.